Good morning and welcome everybody to the second webinar in our series From Biomass to Bio-Based Products. I'm Valeria Mazzagatti from Greenway Europe and I will be your moderator for this webinar. Today we will go through all you need to know about pyrolysis. This webinar is being organized as part of the Bio for Products project. Bio for Products has been funded by the SPIRE private-public partnership under the Horizon 2020 Research and Innovation Programme and is coordinated by Biomass Technology Group, BTG. The project will demonstrate how to transform 4 types of biomass into 4 different bioproducts using pyrolysis as the conversion technology. The scope is to substitute part of the original fossil-based raw materials of these products with sustainable resources and achieve 75% reduction in greenhouse gas emissions. But Hans from BTG will explain more about this later on in this webinar. Here you can see the partners of Bio for Products at the bottom of this slide. Greenway Europe is responsible for the communication, dissemination and exploitation activities of the project. Today we have here 4 excellent speakers that will take us through this pyrolysis journey, addressing topics that range from state-of-the-art techniques to the current status of commercial plants in Europe. And I'm pleased to introduce now Frederick Ronse. Frederick is professor at Ghent University and is an expert in the field of process engineering for thermochemical conversion of biomass in renewable fuels, chemicals, and energy. He will introduce us to fast pyrolysis, explaining how it works and what are its benefits. Frederick, the floor is yours.
Thank you. Thank you for the introduction. So today I will give a short introduction on what fast pyrolysis is and why we should be using it. So pyrolysis basically is the conversion process in which we use high temperatures in the absence of oxygen in order to process biomass into typically 3 different kind of product fractions. So what you end up with is on the first part is a solid residue, which we call a char, which is highly carbonaceous. Then the second product fraction are vapors, which you can condense into a pyrolysis liquid, or also called bio-oil. And then the third product fraction is the non-condensable gases. Now, depending on the process conditions that you apply, you get different yields in each of these 3 product fractions. So hence we can make a distinction between different kinds of pyrolysis processes. So for instance, in the table you can see in this slide, we can make a distinction between fast and slow pyrolysis, as well as some other thermochemical conversion processes like gasification. Now, in fast pyrolysis, typically, we are going to apply rapid heating and rapid removal of the produced vapors. I will come back to that later. And if you do that correctly, typically with a lignocellulosic biomass, you end up with about 70 to 75% in condensable liquid. So 1 kilogram of wood going in results in 0.7-ish kilogram of pyrolysis oil. The remainder is split over the non-condensable gases as well as the char. On the other hand, if you would be heating up more slowly with slightly lower temperatures, so below 500 degrees C, then you will shift the product distribution more towards the solid residue, to the char, and then we talk about slow pyrolysis. Now, in order to understand the proper selection of process conditions in fast pyrolysis, so what it makes a success, you have to understand a little bit about the chemistry that goes on in the pyrolysis reaction. Now, I will not go into full detail, but briefly, what you can say is there's a distinction between 2 groups of reactions. So the first group of reactions that occur during fast pyrolysis is the so-called primary reactions. So basically, these are the reactions responsible for thermally cracking the biomass polymers like cellulose, hemicellulose, and lignin into small compounds like volatiles and gases, and also a small remaining char will also be produced. And these reactions are highly endothermic. Now, if you allow these vapors to remain in the hot reaction zone, they will undergo a second class of reaction, a second group, which we call the secondary pyrolysis reactions. And Typically, what you can say about this second group of reactions is that the vapors are consumed in reactions yielding more non-condensable gases because of cracking reactions, as well as more char because of polymerization reactions. And these reactions are typically more exothermic. So if you would summarize this, so here I have drawn a concept of basically what happens through time in the pyrolysis process. And in the y-axis, you can see basically the solid weights of the material. So you initially start with biomass, and then it undergoes the primary decomposition reaction. So most of the biomass matrix is basically cracked into small volatiles and gases, with a little bit of primary char remaining. Now, this is the primary reactions. If you allow sufficient residence time in the reactor, you get basically the secondary reactions, yielding more char, more non-condensable gases at the expense of the volatiles. So it's clear that if you want to apply pyrolysis, fast pyrolysis, so with the aim of having the maximum yield of condensables, you have to stop your reaction just after the primary decomposition reaction. So fast pyrolysis, we want to stop here just in the middle, so we have the maximum amount of volatiles produced. Slow pyrolysis, to produce more char, obviously you want to also have a maximum extent of secondary decomposition reactions. So that means, to summarize, what are the ideal process conditions for fast pyrolysis? Well, the temperature should be around 500 degrees C, around that temperature, because also in the graph on the right-hand side of the slide, you can clearly see that the liquid yield is around the maximum, around 500, 550 degrees C. Higher temperatures promote more cracking, leading to more gas. Lower temperatures result in incomplete devolatilization, resulting in more solids as well as less condensables. Obviously, you want to reach that temperature at a fast rate, so at a short time. That means that you need to use small particles of your biomass. So that means less than 2 to 3 millimeters in order not to have significant heat transfer limitations. The pressure is typically atmospheric, and above all, the most important thing is you need to be able to remove the vapors as fast as possible, so a very short vapor residence time, in order to quench them into a condensable liquid as fast as possible. The biomass residence time in itself is not that crucial. I mean, you have to allow sufficient time for complete devolatilization. Obviously, you also don't want the char to accumulate in the reactor, because the char can also act as a vapor cracking catalyst. So it's important also to remove the char in due time. So that said, why do we apply fast pyrolysis? What are the main benefits? First of all, it is basically a method to turn a solid biomass into a liquid, with all the benefits of having a liquid. It's easily storable, it's easily pumpable, etc. Additionally, it's also a way to densify the energy content of your biomass. Basically, on a mass basis, pyrolysis liquid has a similar energy density as the parent biomass. So that's around 18 to 20 megajoules per kilogram. However, the bulk density of pyrolysis oil or pyrolysis liquids is much higher. It's about 1.1 kilogram per liter, whereas plain biomass may have a bulk density of several hundreds of kilograms per cubic meter. So that means that sometimes on a volume basis, energy densifications of a factor of 5 to 10 can be reached after applying fast pyrolysis. And a clear example is that picture made by BTG, where you see two measuring cylinders, one containing the raw biomass, the other one containing the pyrolysis oil. Both cylinders contain the same amount of energy. So it's quite clear that there's an energy densification process going on. A second main benefit is that it also solves the logistics of biomass collection and transport. I mean, if you have large biomass processing facilities, one of the big cost factors is collecting the biomass over a wide surface area and transporting it to a central facility. With oil and gas and coal, you don't have that big problem. You have central extraction in a single location, but with biomass, you need to source it over a wide area. So you can think of fast pyrolysis as a way to locally, so take the locally harvested biomass, turn it into a liquid, and then ship it or transport it through tanker trucks to a central processing facility where the bio-oil, for instance, can be upgraded into transportation fuel or into chemicals. Another advantage is that the pyrolysis oil no longer contains the majority of the minerals of the biomass, so that's also a huge advantage, so that you have basically a mineral-free product. And an additional benefit that ties with the previous benefits already mentioned is that the application of the pyrolysis oil versus the production of the pyrolysis oil, so basically the processing of the biomass, that is decoupled in time and in space. And that's a huge advantage given the local availability and also the availability in time of biomass versus the need to process the pyrolysis oil, say, in combustion or in energy production. And above all, it's a very versatile platform. Pyrolysis oil gives a lot of applications, which I will mention in one of my later slides. But first of all, I want to put your attention to what pyrolysis oil actually is. We call it an oil, but it's not like an oil, like in the sense of a fossil oil, fossil fuel oil. It's quite different. If you look here at the table summarizing the composition, you can clearly see it's basically a complex mixture. There is some water in it, I mean, from the feedstock, but also chemically produced in pyrolysis through dehydration reactions. It also contains a lot of oxygenated compounds like acids, aldehydes, and ketones. The acids will be responsible for a low pH. And also some of these compounds may be reactive over time. So that means that for prolonged times, it may not be stable. So that's something you may have to bear in mind, especially when you store it at elevated temperatures. And it's also difficult to distill. That means, that said, that if you want to apply this pyrolysis oil, for instance, as a transportation fuel, that some upgrading may be required. So here you see another comparison between heavy fuel oil and pyrolysis oil. So note the higher water content, the lower pH, as well as the high oxygen content because of all the oxygenated products present in pyrolysis oil when you compare against heavy fuel oil. Now, a little bit more detail about the chemicals present in pyrolysis oil. I will not go into full detail how these chemicals are formed, but it's interesting to note which kind of chemicals are present because some have a commercial value, can be extracted, and can find applications in further chemical synthesis, for instance. So here at the table, you see the maximum quantities reported in fast pyrolysis oil of woody biomass. And it's clear that when you look at the classes of compounds that you see on this table, that you have a group of compounds that originate from the decomposition of cellulose and hemicellulose. Most notably, the anhydrous sugars like levoglucosan is the largest compound to be retrieved in pyrolysis oil and results from cleavage of the cellulose polymer. You also see other sugar-derived compounds like furanic compounds and hydroxyacetaldehyde, for instance. You also see other compounds which are aromatic, basically phenolic. These are indicated with a red dot in my table, and these originate from cracking of the lignin polymer because lignin is an aromatic polymer. So you see compounds like phenol, catechol, syringol. These all have a commercial value and they may be interesting to be extracted from the pyrolysis oil. So that brings me to the slide, what can you do with pyrolysis oil? So how versatile is the fast pyrolysis bio-oil platform? As already mentioned, it has a heating value about roughly half of that of petroleum, so it can be used as a boiler fuel, and that is already commercially demonstrated. I think the speakers also in this webinar will focus on that as well. You can also upgrade pyrolysis oil so it becomes compatible with current engine infrastructure. So we can use it as a drop-in biofuel. That can be done through upgrading, but also through co-feeding in existing petrorefineries. You can also, with some modifications, apply it directly in larger diesel engines and gas turbines. And also, finally, you can also think of chemical applications where you extract individual chemical compounds or classes of compounds for further chemical synthesis or application. And finally, in my presentation, I also have a couple of slides on how we can apply pyrolysis in a more large-scale setting. So what kind of reactor systems have been developed so far and have been demonstrated to work on a commercial scale? Well, there are basically 4 large systems or reactor systems developed, 2 of which depend on fluidized beds. So basically the idea is that you have a bed which is suspended in a hot gas stream of carrier particles. So you have like sand being suspended in hot gas. And in that hot bed, we inject our biomass particles, so the rapid heat transfer between the hot sand particles and the biomass particles results in the pyrolysis reactions taking place. Afterwards, the carrier gas mixed with the vapors and gases needs to be separated, needs to be condensed. The non-condensable gases can be burned to provide energy, and then the condensate can be exported as pyrolysis oil. A slight variant on this process is a so-called circulating fluid bed. So where basically you employ higher fluidization gas velocities. So you have a kind of a loop system. So here you can see it on the right-hand side of my slides, where you have a riser carrying hot sand and or any other hot carrier material and hot gases. The biomass is mixed. During the rising action of this material, the biomass reacts, resulting in char, condensable vapors, as well as non-condensable gases at the top. We separate, obviously, the solids with a cyclone. And then typically also integrated in that loop is the mixture of char and sand flows back into a char combustor where the char is burned to reheat the sand and to feed it back to the bottom of the riser. The volatiles and the gases are then further separated, quenched in a condenser. And also here there are typical examples like Ensign and VTT who have demonstrated this technology already on a larger scale. And then finally, or third, I come to a technology which will be mentioned also in more detail during this webinar because it is a technology developed by BTG itself, which is a rotating cone reactor in which we have a spinning cone. At the bottom, we add, again, hot sand and biomass, and then through the centrifugal action, the mixture is mixed, the pyrolysis reactions ensue, and then at the top, we collect, again, the char-sand mixture, as well as the volatiles and the gases. Again, also the char is combusted to provide process heat to reheat the sand, so you also have a kind of a loop system so that keeps the process going. And again, also here, the Empyro project is a nice example of a commercial application, but I'm pretty sure that will be detailed later. So I will move over to the last type of reactor system that has been developed commercially. I would not say commercially, it's more on a pilot scale. That's the auger reactor, in which we use an Archimedean screw to basically push a mixture of hot sand and biomass, let it react, and then separate the vapors and the gases from the char solid mixture. This technology cannot scale as high as the other three previously mentioned, so it's a bit more limited because of mechanical complexities. So far it only has been demonstrated more on a pilot scale level. And that brings me to the end of this introductional session, I would say, during this webinar. I have a couple of conclusions. So first of all, fast pyrolysis, basically what you have to remember, it's a technique to turn a solid biomass into a liquid product. So it's a kind of a pretreatment technology. Basically, the success of fast pyrolysis is selecting the proper reaction conditions, so to have high liquid yields. And it results in a very versatile platform for both fuels, energy, and chemicals. And also, it already has become a mature technology with commercial examples available. And I have no doubt this will be further highlighted during the next speaker sessions. I thank you for your attention. So I think we still have some time left on the clock for some brief questions.
Indeed, thanks a lot, Frederick. It has been a very comprehensive presentation, and we have already a few questions here for you. One is, a person is asking if you can say anything about the utilization of catalysts in pyrolytic technologies. For example, how do catalysts influence yields of liquid, solid, and gaseous products? And another question is, what type of biomass, apart from the woody biomass, can be processed using this technology?
Okay, two very interesting questions. So I will first tackle the first question. So catalysts can indeed be used. We call this process then catalytic fast pyrolysis. I haven't introduced that in my slides, but the idea is to basically change the composition of the vapors, basically have less oxygen containing vapors. So you want to apply a catalyst so that you have more hydrocarbons like aromatics or aliphatic hydrocarbons in your product after condensation rather than these oxygenated compounds. So the idea is to have a more stable oil with less oxygen. This is possible, so you can do that, for instance, by applying zeolytic catalysts into the process. Obviously, this comes at the expense of the yield. So first of all, just removing the oxygen reduces the yield in itself because you're basically taking away mass out of your condensable product. But also the yield goes even down further because what we see in these processes, the carbon yield, so basically how much carbon ends up in your product of interest, being your liquid, versus the carbon going into your with the biomass, that carbon yield also goes down, and that is because a lot of these catalysts are prone to coking. So that's basically a carbon loss. So this is something to keep in mind. But this technology also has been tested already on a fairly large scale, but it comes at a yield penalty. The advantage is you have a more stable oil that may be easier to be co-fed into petrorefineries. The second question regarding the biomasses that can be used in fast pyrolysis. So typically right now, large scale applications typically run on woody biomass. There is a reason for that. Woody biomass has a low ash content. And this is a bit of a problem. So if you go to residues, for instance, from agriculture, for instance, like grasses and straw, there you see higher ash contents. And what you end up with is that these ashes, they might accumulate into your system, and they cause also a drop in pyrolysis oil yield in time. So what happens is some of these ashes, like potassium, like calcium, they can also be a bit catalytically active in a bad way. So they reduce the yield in condensables, specifically the condensables of interest. So this is unfortunately also some research question that still needs to be tackled. So to guarantee long-term operation on, let's say, more ash-rich biomass feedstocks. So I hope that answers both questions.
Great, thank you very much. We are a little bit, we have to carry on with the schedule. So there are several questions here that they are all very interesting, and we won't have time to answer now. But I'll keep them for the end of the webinar to see if we have more time. And otherwise, for all the people that didn't have their question answered, they can write directly to Professor Ronse. You can see the email there, so I'm sure Frederick will be happy to answer. So we move now on to the next presentation. So Gerard Muggen. Gerard is Managing Director at BTL Bioliquids, which is a small company dedicated to the worldwide commercialization of the fast pyrolysis technology developed by BTG. BTL Bioliquids has been running the Empire fast pyrolysis installation in Hengelo in the Netherlands and sold 2 new projects in Finland and Sweden. Gerard will present the current market status of pyrolysis plants in Europe, drawing on his first-hand experience in this field, and I'm sure some of the questions of the previous session can also be answered. Could also be answered by Gerard concerning commercialization. So please, Gerard, the floor is yours.
Good morning. It's a pleasure to be here and to present our pyrolysis technology to you. Okay, yes, who we are. We consider ourselves as a technology provider and product leader. So we will not produce pyrolysis oil anymore. We are providing pyrolysis plants. We have showed our technology on the plant Empyro. In that case, we were the producer of pyrolysis oil, but we have sold this plant to Twente. So now we are really concentrating on the sales of the pyrolysis plants. For most people, it's obvious, but we only use second-generation biomass, not competing with the food chain. We only using residues. Something about our history. BTG BTL is selling the technology originally invented by BTG. And what I want to express in my presentation is all about the people. Of course, the technology is important, but technology would not have been there if the people would not have been very active in the last even 25 years working in this technology. The interesting thing about this screen is all the pictures you see of the people, except for one, are still working with pyrolysis oil. So it's extremely important to have a good people on board who are doing not only the technology, but also do the marketing and sales, And yeah, that's the crucial thing about developing something new. Very short, having explained already by the previous speaker. Yeah, what we are doing is we're heating our biomass to around 500 degrees Celsius. It's a kind of mechanical mixing of hot sand and biomass. So we're creating a kind of oily smoke, and this oily smoke is condensed in our condenser, as shown in this picture. It's not moving here, but I tried to explain to you. You can see here the reactor. You can see the biomass coming from the top, and we are circulating the sand. After the oily smoke, which is condensed in our condenser, we still have char, and we're burning the char in our combustor. The advantage of the total concept is that we're not only producing oil, but we're also producing electricity and heat. The heat is sold in the case of Empiro to AkzoNobel, currently Nourion, and the electricity is put on the grid. Advantage of the concept is that when we are running, we do not need any external energy anymore. So the process is driven by itself. Total efficiency is in a range of 85 to 90%. It's quite efficient, so we're converting 5 tons of biomass with a yield of around 65%. So around every 1,000 kilos of biomass is converted into 650 kilos of oil, and the rest is used for heat and power. Empiro was our first commercial plant, so it's of course very exciting, with financial close in December 2013, and the first oil was produced in March 2015. It's costing time, as you can see in the graph here. To give you some idea, we were very proud that we have produced in the first year around 1 million liter of pyrolysis oil, and now I can tell you that we are producing 1 million liter every 2.5 weeks. So it's going very smooth. At the other end, you can also say that it's costing time. So it cost us around 3 years to reach the running hours which we would like to have. That's extremely important, to have this patience and to do everything step by step. As you can also see here in this graph, at the moment we're producing 3.3 tons of oil per hour, around 7.5 megawatt of steam, and around 650 kilowatt of electricity. Now, again, the start of Empiro in March 2015. Plant runs now steadily. We're even thinking to run the plant unmanned in the nighttime, so it's very smooth. It's now operated by Twence, by the way, which is also smooth. Exciting was that in April 2019 we have sold our first plant to Finland, to Greenfield Nordic. This oil will be used for boiler and heat applications. In September 2019, a new pyrolysis plant was sold to Pyrocell in Sweden, and the exciting thing in this project is that pyrolysis oil will be used by Preem on their refinery. It's the first project in the world where pyrolysis oil, the crude pyrolysis oil without upgrading, will be used by Preem. To pyrolysis oil application at Friesland Campina, we are replacing around 10 million cubic meter of natural gas. The heat is used for dairy projects, and the total greenhouse gas reduction is around 93%. Commercial rollout, as I mentioned to you before, Empiro was built, also financed by ourselves. Sold it to Twence last January. You can see the plant in Finland, Greenfield Nordic, Lieksa, very close to the Russian border, and Pyrocell, etc. Interesting thing about these both projects is that we're using sawdust as a feedstock. We're building the pyrolysis oil plants very close to where the biomass is, as also described by the earlier speaker. We believe in the decentralized conversion of the biomass to the crude oil and transport the oil, and then you can use the oil anywhere you like in the world. So that's the concept. I do not believe in complicated transfer processes close to the biomass. So a conversion process. I do not believe in catalyst. Don't believe in hydrogen. Of course, it's possible, but it should be done in a central, larger location. So don't play decentralized with catalyst and with hydrogen. Working together with Technip. Technip is crucial for the rollout of our technology. So BTG BTL will concentrate on the core technology, and Technip, which is one of the largest worldwide engineering and construction companies in the world, they will help us with the, let's say, the local commissioning and the engineering and the actual delivery of the turnkey contracts. This picture is made by BTG. What I like about this picture is it's a kind of overview of what are the possibilities with biomass. On the left side, you see the biomass itself. On the right side, you can see all the, let's say, applications, but also the added value. I like to do these presentations all over the world. I typically ask the audience where you want to be. Everyone says, oh, I want to be in the high added value applications. Of course, it's good. Also, Hans will tell something about it, but I strongly believe it should be done step by step. So I do not believe in a future where you only see the bio-based material without the use of pyrolysis oil or the residues of the pyrolysis oil for the power and heat generation. So do it also this step by step. Start with heat and power, make more and more volume, and step by step climb the ladder with the higher value applications. This is the application at Friesland Campina. It's a boiler. Interesting thing about this boiler, it's co-firing of pyrolysis oil and natural gas. It can be switched over from one fuel to the other within seconds. That's the advantage of the concept. Whereas if you have a biomass boiler, it's costing more time to produce steam from the biomass boiler. This pyrolysis oil, it can be extremely fast. It can all be the volume of the boiler is a lot smaller. So that's it's actually a big logistical advantage to use pyrolysis oil on a boiler rather than biomass. In this picture, we see also here a kind of step-by-step approach. You can see if you want to bring pyrolysis oil to a refinery, we have the first step now done with, we're doing the first step now with PREEM. You can see the green arrow, the fast pyrolysis bio oil. It's untreated pyrolysis oil. We don't do anything. It's directly coming from our plant, and we're mixing it until around 5% of the FCC rate. So that's a very important one. It's one of the most cost-effective routes to go to a refinery, and with this, refineries are easily complying with the Renewable Energy Directive. Suppose you want to go to a larger percentage, then you need to upgrade the pyrolysis oil. BTG have developed a catalyst called Picula, and then you can reduce the amount of oxygen in the pyrolysis oil, and you still can go to a refinery and do the last step in the refinery. This morning, BTG have announced they brought out a press release where they have indicated that they are now want to go to transportation fuels for shipping. Very exciting development. It means you would have 4 to 6 pyrolysis plants bringing the crude oil to such a larger upgrading facility, and after this you can use the fuel coming from there to use for maritime applications. Very exciting. Just announced this morning. Co-feeding of pyrolysis oil, the crude pyrolysis oil, is extremely simple. You only need to make a connection to the riser of the FCC. By doing that, you can see on the right side that the green molecules will go to the dry gas, LPG, but of course most important to the gasoline and also to the diesel, and also part is going to the slurry oil. As indicated before, it's one of the most cost-effective ways to go to a refinery. My last slide summary. I will not read everything to you. The third bullet is interesting. PREEM is showing that it's possible to go to a refinery. Also the fourth bullet, co-processing fast pyrolysis bio oil, is a very interesting way to go to until this 5% to go to a refinery. Okay, that was all. Yeah, this is my presentation, so you can read it on the presentations will be sent out, so you can read it carefully after this seminar. Thank you very much.
Thank you very much, Gerard. Also very interesting presentation, and also here lots of questions. I pick up one, which is like, which obstacle do you see for widespread application of pyrolysis?
It's a kind of challenge. So the pyrolysis technology itself, it's now proven. So that's not the issue. It's very important that people now start to work on the application of the oil. So first of all, it was very important that we prove that the production of the pyrolysis oil is possible. That's what we have now done in Empiro and to continue to do in Sweden and Finland. Now it's very important that more and more refineries will allow the pyrolysis oil in their refineries.
Okay. Also, another question. Are you thinking or are you ready to take a project outside Europe? There is a question from India, for example, some interest from India.
Yeah, of course, let's say the world is our territory. There is only one important question which I always ask. Is there any, typically you need a kind of CO2 tax for the use of pyrolysis or an obligation to blend. An obligation to blend is of course very important. In Europe, there is such a situation. I'm not an expert in India, but I know in India the Indian government is promoting the second generation ethanol, and the laws are in this direction. As far as I know, there's not yet a law for using pyrolysis oil. So we are open to go anywhere in the world, but my first question would always be, is it profitable for customers?
Of course. And of the chemicals found in the pyrolysis oils, which one have you identified as highest, as having the largest market potential? If you
That's an
this
interesting.
kind of analysis.
Yeah, Hans will come back on the different applications.
Okay.
For me, it's very difficult to say because a lot of people ask me, what is inside pyrolysis oil? I turn the question around, what do you want to have? There's a lot inside. It's a kind of telephone book of all kinds of different molecules. Once again, you have to go there step by step. And what is the most interesting? Yeah, sorry to say, but yeah, the future will tell. I don't know.
Okay. Another question, do you have any experience with using food waste as feedstock? And what kind, yeah, and is there other bio-waste that you can use with pyrolysis?
Yeah, food waste, it depends on what it is. I would say, let's say agro residues. That's of course perfect, but also as indicated earlier, in agro residues there are more minerals. So minerals are a kind of challenging. Pyrolysis oil is a technology which can handle that one, but we have found out that it is very important to wash the biomass first. It will remove part of the minerals, so that's a good one. Advantage of pyrolysis, generally speaking, that we are operating at 500 degrees Celsius. So that's, for example, potassium will not melt at those temperatures, so that's an advantage. If you talk about real food waste, we didn't. If you, for example, if you use, if the people asking the questions, meaning, for example, bread residues, we didn't try. But for example, corn stove we have done, straw we have done. So those kind of applications are possible. It's now more an economical question than a technical question. So if the prices are low, then it's okay. But to give you an example, straw prices in Denmark are around 100 euros per ton. So sorry to say, but then it doesn't make any sense to use straw as a feedstock. The straw in Ukraine is around 5 euros per ton. That makes sense. So it's more an economical choice than, and it should be kind of logical. If the stream is extremely wet, then it's better to digest it, and then pyrolysis oil doesn't make any sense.
Okay, I think that answered the question. There is another question about if there is the possibility to have small-scale plants that are mobile, for example, shipping container size, because the person is asking, is underlining that is relevant for developing economies where there is a transport logistic cost.
Yeah, this is an intriguing question. I love the question a lot because that's also what we are thinking every day. Let's say the idea of mobile pyrolysis is very charming, but there are some challenges. The challenges I see is the fact that it's more difficult to do good heat integration. It's more difficult. Let's say we also earn at Empire quite a lot of money by selling the steam to AkzoNobel. So heat integration is more complicated. And I'm a bit afraid that the quality of the pyrolysis oil will be challenging. I'm not saying bad, but challenging. Suppose that you would do it in a farmer's area and the end product pyrolysis oil could directly go in a tractor. Then I would say yes, that's an interesting one. But still the pyrolysis oil have to be collected then from all those very small locations. So I'm not against the idea is very nice, but I doubt about the technical and also the commercial feasibility, to be honest. And if you design a plant in the size of what we have done, 25 megawatt, you can decently transport, let's say, biomass around 50 kilometers, 50. And then you have a very sustainable solution and also cost-effective solutions. And I believe that's a smarter way than to travel with your pyrolysis plant on the tractor or truck.
Perfect. Thank you very much. I think we have now to move to the next speaker. Once again, if we have time at the end of the webinar, we will answer some of the questions that are that have been asked. Otherwise, you can see here the email address of Gerard. You can contact him after the webinar in case he didn't answer the question.
Yep.
And you can have a direct exchange with him. Thanks a lot, Gerard.
Okay, thank you.
We now move to Paul de Wilde. I had the pleasure to introduce him. Paul de Wilde is a senior scientist in the field of biomass and energy efficiency at the Energy Research Center of the Netherlands. He has been working on pyrolysis research for several years, and today we'll talk about fractional condensation of biomass pyrolysis vapor. Paul, the floor is yours. Thanks a lot.
Thank you, Valeria, for the nice introduction. Good morning, everybody. I would like to present, let's say, a real life or real laboratory example of the valorization of biomass and with the focus on the valorization of lignin. The project on which I'm going to talk is conducted, it's still running, and it's conducted in the framework of the Biorefinery Shared Research Center in the southwest of the Netherlands, with a focus on extracting or producing functionalized aromatics from biomass, and especially from lignin, let's say, or lignin-rich biomass types. So the contents of my presentation are as follows. I will first shortly introduce the concept of fractional condensation of biomass pyrolysis vapors, with a focus on the lignin and lignin-rich biomass types. And then I will spend a few slides on explaining the Calibra project, which is currently still going on, as I talked before. It is a national project. It's an acronym. It stands for Cascading Lignin Biorefinery Approach, and it's focusing on the pyrolysis of biomass, lignin-rich biomass, for applications, for products that can preferably directly be used for, let's say, medium value, high volume applications. And of which, and I completely agree with the previous speaker, of which heat and power are, of course, also products that are important. So I will shortly introduce the project. I will tell something about the experimental approach that we use, and then finally some results discussion, and I will end with the conclusions. So fractional condensation, as has been quite nicely explained by the previous speakers, pyrolysis is not a simple process. If you pyrolyze biomass or lignin, you get really a very complex mixture of products, both solid products like the char, but also gaseous products, that what we call normally the hot pyrolysis vapors, that consists of non-condensable gases like carbon monoxide, methane, carbon dioxide, and then a whole bunch of, let's say, organic molecules that can be, in theory, can be condensed. And this is basically the target of my presentation. We want to see if we can use the concept of fractional condensation to split this very complex mixture of organic condensable material that also contain aerosols, and these aerosols also consist of different types of chemicals. If we can use fractional condensation to split this complex mixture into a limited number of fractions, with specific characteristics that are good for direct application for specific end users, of which I'm going to tell a little bit later. So the final goal of the project is to optimize the recovery of the condensable pyrolysis vapors in a limited number of fractions through a dedicated fractional condensation approach. Condensation, obviously, is based on chemical and physical characteristics, for instance, dew point and also electrostatic interactions between the molecules and the fractions in the hot pyrolysis vapors. So the concept of the Calibra project is that we, starting from some lignin or lignin-rich biomass types, for instance, agro-food or steam explosion lignin from biorefineries, second-generation biorefineries. We have a pyrolysis reactor. I'm going to tell a little bit more about it later. And we have a condensation train consisting of several condensers, which are each of them individually are more or less state-of-the-art condensers. Electrostatic precipitation is also an important separation part of separation equipment. And then finally, we can collect several fractions that are in view of applications like additives for bitumen, for high quality roofing bitumen, as additives for shipping fuels, as also the previous speaker mentioned, or as feedstocks for extracting high value chemicals. So the aim of the Calibra project is to deploy a cost-effective valorization route for especially lignin residues, so especially going to aromatic chemicals. Experimentally verify the feasibility of the process to see if we can get to some viable business cases in close collaboration, I should say, with some important industrial partners, and also to lay the framework, to lay the foundation for further scale up of the reactor technology, but basically further scale up the fractional condensation technology. So in contrast to the next speaker, which is basically very interesting on this webinar, we apply in situ fractionation, which means that we try to select specific fractions directly after the primary pyrolysis process. And obviously, also there's also a residual fraction that can be used for heat and power, but we want to catch the valuable fractions as soon as possible, which is somehow in contrast to another approach, which is evenly valid, is to first make pyrolysis oil and then in the downstream processing steps extract chemicals from that previously produced pyrolysis oil. Okay. We are currently doing experiments. We are using a somewhat different type of reactor, as has been explained by the previous speakers. We are using what we call the pyrolysis reactor. This has been developed at ECN, at TNO. It's basically an integrated system in which pyrolysis and combustion of char are combined, which gives us the advantage that we have a direct and a useful application of the char in a combustion in a surrounding bubbling fluidized bed. The combustion of the char generates heat that can be used for the primary pyrolysis process that takes place in a riser reactor. Now we're talking about, it's still fluidized bed, but I would say it's more tending towards entrained flow pyrolysis. Then we have downstream the reactor, we have a fractional condensation train consisting of a hot particle filter, a heated Tarnock output to catch the more heavy molecular weight products, and then a heated electrostatic filter to catch the aerosols, and finally some cooled condensers. I will present some results on two types of agro-food residues, coca shell granulates and walnut shell granulates, and I will present some examples of a typical lignin-rich biorefinery residue produced from straw. So, as we all do, we start with some analysis, and just to show you this graph is these three types of biomass are relatively rich in lignin. We also have been doing tests with pure lignin, but that's a little bit beyond the scope of my presentation. And if you have questions about that, you can always ask me. But you see, these three types of biomass are relatively rich in lignin. This is the test rig setup that we currently use. We have this pyrolysis reactor. We have a filter to catch out fine char particles and dust and ash. that is not combusted in the reactor itself. And then we have a train of condensers. We start with a high temperature condenser, then we have a relatively high temperature or mild temperature electrostatic filter. We have a cooled condenser, basically a gas cooler and an intensive cooler to take out the final traces of low boiling components. And finally, we do not do that at this moment in the small laboratory scale test rig, which is typically a few kilograms per hour. But in a more, let's say, scaled up version, you can use the pyrolysis gas, which is a low calorific value gas. You can use that for combustion to generate some extra heat. Okay, well, this is an example of our current fractionation equipment. You see here, for instance, the electrostatic precipitator, Charnock output, some condensers, and my operator who is waiting for the first drops of oil to condense in the different collection flasks. Some first results of the three biomass types that I introduced. So the walnut, the granulated walnut shells, the cocoa shells, and the dried distilled biomass, which is basically a biorefinery residue. So we have basically four fractions. We have a fraction that we collect at around 100 or somewhat higher than 100 degrees centigrade. We have a fraction that we condense in the electrostatic precipitator. And we have two fractions that are more containing the water and the low boiling components at 4 degrees and at low temperatures. So what you can see here is that the largest fraction is collected in the electrostatic precipitator. A small heavy molecular weight fraction is condensed in the high temperature Charnock output. And considering the mass yield, the largest fraction is condensed in the low temperature condensers, which mostly containing water. So this is how typical fractions look like. These are, let's say, quite high viscous types of pyrolysis oil. Low viscous types of pyrolysis oil containing quite a lot of water. And of course, we get some condensation of char or heavy molecular weight material on the first Charnock output filter. Of course, since we are focusing also on high value chemicals, we do some analysis on the several fractions, and you can see here in these three graphs for the three types of biomass, you can see what kind of typical chemical products you get. For instance, it's immediately clear that there is already a kind of a separation between the aqueous, between the water and the high molecular weight fractions. So the water is obviously collected in the lower temperature fractions, while the more heavier molecular weight material is collected in the higher temperature fractions. And there is also already a separation, a partial separation between high molecular weight and low molecular weight fractions. And at this moment, we are not really focusing on individual chemicals, because there are, just like Gerrit was explaining, there's a whole telephone book of materials present. And as we have been noticing in collaboration with industry, also mixtures of, let's say, similar families like phenolic compounds can be used, for instance, in phenolic resins or in bitumen to replace asphaltenes. And there are plenty of applications already for this directly recovered fractions. And it's also an advantage that you do not necessarily have to deploy difficult downstream separation technologies. So finally, at one of my last slides is we can play around. The test rig that we at this moment deploy is very flexible in choosing temperature and gas flow conditions. So by playing around with temperature, we can also steer the amount and also a little bit the composition of the fractions that we collect at specific temperatures. And that is explained here. For instance, if you have somewhat higher temperatures, you get somewhat more mild cracking, so you get somewhat more lighter and low boiling components in your low temperature condensers. So finally, I would like to acknowledge also some of our industrial partners that are also collaborating in this project and that are also partly doing application trials. We have Olam, important multinational company that provides, for instance, coconut shell feedstocks. We have the company Enopy, a small pyrolysis company that is working together with us to scale up the pyrolysis process and the condensation, the product recovery part of the test rig. We have a university to do some more fundamental analysis and upgrading work of some samples. And we have three industrial partners that are working on upgrading, extracting a further extraction of materials from specific pyrolysis oil fractions. We have the company Good Fuels that reviews the quality of the of specific fractions for use in marine fuels, and we have the French company Soprema, who is testing other lignin pyrolysis oil fractions for using as an additive in bitumen. So this brings me to my last slide, conclusions. So at this moment we are relatively confident that we can apply a relatively straightforward staged condensation system to separate the pyrolysis vapors in a limited number of usable fractions, directly usable fractions. There, of course, obviously, there are still some challenges in getting the separation better. So not too much lighter material in the heavy molecular weight fraction and vice versa. And as we have been noticing in the last year of this Calibra project, it seems indeed possible to use this directly recovered fractions, for instance, as a replacement of bisphenol A in specific epoxy resins, or to mix up to 50% of another heavier molecular weight fraction into a petrochemical bitumen for making roofing bitumen for asphalt. And well, finally, we are almost ready with scaling up to a factor 2 or 3 of the test truck for producing larger samples for, let's say, further application trials of the fractions that we collect. And obviously, there is also a residue fraction that is still in view to generate heat and power from. So with this, I would like to conclude my presentation. Thank you for your attention, and I would be happy to answer some questions.
Thanks a lot, Paul, for the presentation. We are a little bit late, but we have time for I pick up just 2 questions. One is about the fact that although you're not looking at the individual components at the moment, is there a specific chemical you hope to obtain from the oil that is high value? For example, levoglucosan or a specific type of lignin derivative component. And the other question is about biobitumen. Can you use biobitumen directly as marine fuel, or is it miscible?
Yes, those are 2 interesting questions. So to start with the first one, indeed we are not focusing on a separate individual chemical, but we are definitely focusing, targeting phenolics as a family. And especially, for instance, alkyl phenolics are a very interesting group of chemicals because they can be, and has been proven, they can be used in a good way to replace phenol, for instance, in phenol formaldehyde resins. Also a, let's say, aromatic fraction that we collect, that's one of the, let's say, higher molecular weight fractions, appears to be very suitable for replacing bisphenol A in the production of epoxy resins. So that is at this moment our focus. Regarding more, let's say, specific chemicals, some chemicals end up in the more, let's say, aqueous fractions. And there are some possibilities by means of filtration or crystallization to go for separate chemicals, but then you can think of things like acetic acid or some water-soluble phenols. That's possible. The second question about biobitumen. Well, actually, we collect a very, let's say, almost solid fraction, but it's not a char. It is still a almost solidified pyrolysis oil that seems to be very good suitable for as an additive in the formulation of rubber. The second fraction, which is more like a paste, is in view for using it in biobitumen. But as we have seen, it is also miscible with a commercial bunker fuel, a commercial heavy fuel oil that's currently used and that's currently a fuel for marine applications. So yes, that is possible. And we are now striving with using a larger, an upscaled version of our condensation rig to produce enough samples to really produce so much material to have a real engine test with this, let's say, bio-based blend. So I hope this answers the questions a little bit.
Thank you very much, Paul. It's been very interesting. And once again, there are other questions that are unanswered. So here there is the email address of Paul. You can write to him directly if you have still questions you would like to be answered. Thanks a lot.
Okay.
And now, last but not least, our first speaker, Hans Herrens. Hans is a process engineer at BTG Biomass Technology Group. BTG is a Dutch SME company with a broad expertise in the thermochemical biomass conversion processes like fast pyrolysis, gasification, and torrefaction. BTG is currently putting a significant effort into the development of processes for the production of biofuels and bio-based products, mainly using fast pyrolysis oil as feedstock. Today, Hans will present the state-of-the-art in fast pyrolysis oil fractionation, including the latest findings of the Bio4Products project. Hans, the floor is yours.
Yes, thank you, Valeria, for the introduction. So today I will tell something about the thermochemical fractionation of lignocellulosic biomass. So first I will give a short introduction and the objectives of the Bio4Products project. In Bio4Products we do quite a bit of thermochemical fractionation. Then a little bit more about fast pyrolysis bio-oil fractionation. I will also give a short description of the individual pyrolysis oil fractions and something about their properties. Then I will tell something about fractionation on bench scale and fractionation in the new pilot plant we have at BTG. I will tell something about the design and construction of the pilot plant and on the current status. And finally, a short summary. So Bio4Products, it's EU Spire funded project. It started at the 1st of September in 2016 and will run until the 1st of September in 2020. In Bio4Products, we want to convert biomass from 4 different kind of bioresources by thermochemical fractionation into intermediates which can be used in 4 different applications. In Bio4Products, we also want to design and construct and operate a pyrolysis fractionation pilot plant, which is able to process 3 tons a day of pyrolysis oil. So here we go from bench scale TRL level 4 to 6-7. Different applications. We have different partners who are looking at different applications of the fractions, and they will be demonstrated in 4 end products. We have a partner Hexion, which will look at the replacement of fossil phenol with 30 to 65% of pyrolytic lignin in 2 types of resins. So this is a foam resins and a molding resin. Then we have TFC and Foreco, which will look at the replacement of, for instance, creosote up to 100% by pyrolytic sugars to modify wood. TFC is also looking at the application of the pyrolytic sugars to replace 30 to 65% of furan-based foundry resins by the pyrolytic sugars. In Bio4Products, we also look at the technical and economic and environmental assessment of the whole value chain. In Bio4Products, Capax is providing us with the biomass, and we have Evotech looking at the business feasibility, and Greenovate will do the communication and dissemination. So a little bit more into the thermochemical fractionation. If you have biomass, a lignocellulosic biomass, the main components you have in the biomass are cellulose, lignin, and hemicellulose. Depending on the type of biomass, you might also have some extractives. In fast pyrolysis, this biomass is converted to depolymerized components. And if you fractionate this pyrolysis oil, you will produce different fractions containing pyrolytic acids, pyrolytic sugars, pyrolytic lignins, and the extractives. So in thermochemical fractionation via fast pyrolysis, these key biomass functionalities are retained in these fractions. The fractionation process in thermochemical fractionation is based on a liquid-liquid extraction. enables the separation on basis on functionality. Each of these fractions produced in thermochemical fractionation can directly be used as a raw material in all kinds of bio-based products, but can also be a starting point for further dedicated conversion. In thermochemical fractionation, we do not make any byproducts or waste. Excess fractions produced can be mixed back in the pyrolysis liquid, which can then be used as a fuel, liquid fuel. So in bioproducts, we tested many kinds of different biomass feedstock in thermochemical fractionation. Here in this figure, some of those biomasses are illustrated. So this figure shows the yield of thermochemical fractions. So we first apply fast pyrolysis to the biomass. So we make gases. Typically, about 15% of the biomass is converted to gases, 15% is converted to char, and we also make some ash, which originates from the minerals in the biomass, and up to 60 to 70% of the biomass is converted to the pyrolysis liquids. If you look at the pyrolysis liquids, 1 to 3% consist of extractives, up to 30% consists of the lignin, and up to 40% consists of the pyrolytic sugars. Let's go a little bit further into the fractions. So here we have the first fraction, the extractives. They originate from resin and terpene and fatty acid material in the biomass. The extractives is a little bit thick, dark, tall oil-like liquid. We also had a look at the composition. We applied multiple GC analyses on the extractive. So in this table, you also see some of the analyses done on extractives obtained from different kind of pyrolysis oil. Typically, what we see in GC analysis is that we for example, look at the pine wood extractives, that we could analyze about 40% of the extractive. So this is the volatile fraction of the oil. This means that about 60% of the oil of the extractives could not be determined by a GC analysis. We also did, for example, carbon residue analysis on these extractives, and these analyses show that typically we obtain values of about 2% of these extractives, meaning that the largest part of the extractives are distillable. We need to do some further quantitative analysis here on the extractives. If you look at possible applications for the extractives, you have to think about the specialty chemicals, but it can also be used as a co-feed in HDO to produce diesel. So then we go to fraction 2, the pyrolytic sugars. So in pyrolysis, the cellulose and hemicellulose polymers, they are cracked to sugar monomers, oligomers, and polymer fractions. So if you look at the monomers, it's mainly levoglucosan. So this is the anhydrous sugar of glucose. We also make some cellobiosan, which is also an anhydrous sugar, partly. In thermochemical fractionation, we can produce this pyrolytic sugar as an aqueous solution, including acids and ketones and aldehydes. But we can also further concentrate it to make a syrup, which is also shown in the photo. So properties. So we have a water content between 4 and 65%, and it's also a mineral-free fraction. Then we go to the third fraction, the pyrolytic lignin. As for the pyrolytic sugars, the pyrolytic lignin is also produced by partly depolymerizing the lignin. So it consists of monomers, oligomers, and polymer fractions. Pyrolytic lignin is a highly viscous liquid. So in the first picture on the left, you see a photo of the pyrolytic lignin straight out of the extractor. It's also mineral-free and has a relatively low molecular weight, average molecular weight. So the pyrolytic lignin straight out of the extractor has an average molecular weight about 840. So this is much lower when you compare to natural or craft lignin, which is can be between 1,000 or 8,000. The pyrolytic lignin is soluble in many different solvents like ethanol, methanol acetone, and sodium hydroxide solutions, for example. It also showed to be more reactive than other lignins like natural lignin or craft lignin. but less reactive than phenol. We can also convert this liquid pyrolytic lignin into monomeric pyrolytic lignin. This fraction consists mainly of guaiacols, acylphenols, and cyclohexanols. Also, we can convert this pyrolytic lignin to a solid pyrolytic lignin. By doing this, the average molecular weight is increasing. So the solid pyrolytic lignin has an average molecular weight of about 1300. It also has a softening point of about 130 and a melting point of around 160. So this thermochemical fractionation we can do in a continuous bench scale unit at BTG with an input capacity of 12.5 kilograms an hour of pyrolysis oil. This bench scale unit consists of two liquid extractors. So we want to separate the oil in the extractives. We want to split up the oil in an aqueous sugar phase and a liquid lignin phase. This unit you see here in the photo is operational since 2011. It's operated at ambient pressure and at temperatures up to 70 to 80 degrees C. We tested many different pyrolysis oils produced from different kinds of biomass feedstocks, which were produced in our bench scale and pilot scale fast pyrolysis units. So making all these fractions also initiated the development of bio-based products. And this bench scale fractionation unit was also the design basis for the pilot plant. So in bio for products, not only the fractionation is done on pilot plant, but also the development of different kinds of products from the fraction will be demonstrated on pilot plants. So partners needed large amounts of raw material, which means we had to build this pilot plant. We were scaling up our continuous bench scale unit, so this 12.5 kilograms an hour unit, to a pilot scale of 125 kilograms an hour oil input. The heart of this pilot plant are also two liquid extractors. It also contains multiple concentrators, for example, to recover and to recycle the extractants used in fractionation. We also have a possibility to treat the pyrolytic lignin to produce a solid pyrolytic lignin. This unit is placed next to our pyrolysis pilot plant because the input of the fractionation plant is the output of the pyrolysis pilot plant. So the pyrolysis pilot plant is able to produce 3 tons a day of pyrolysis oil, and this fractionation pilot plant is able to process 3 tons a day of fast processed bio oil. So as you can see in this picture, our compact 3-level design was made because of limited space in our laboratory. And then we started to construct the fractionation pilot plant. You see some photos here on the left, which are of the finished pilot plant. The construction was completed in the summer of 2018, and we did commissioning of this pilot plant at the end of 2018. Now we do all kinds of test runs, also to further optimize the fractionation, for example. And we now reached a capacity of around 105 kilograms an hour of oil input, which means a design capacity which is about 84% of the design capacity. We also had a look at the properties and the yields of the fractions produced, mainly the lignin and the sugars, and these are similar to the fractions we produced in our bench scale unit. A bit more about the fractionation pilot plant. It actually consists of 5 separate processes. So we have one section in which we do the oil extraction to remove the extractives. Then we have the oil fractionation section in which we split up the oil into the pyrolytic sugars, aqueous pyrolytic sugars, and the pyrolytic lignin. Then we have a section in which we process the aqueous sugars to produce the sugar syrup, and in which we retrieve the extractives from the extraction solvent. Then we have a section in which we do the lignin processing, so we convert the liquid lignin into the solid pyrolytic lignin. And we also have a section in which we can do liquid handling, so pumping, for example, add oils and retrieve the products. This pilot plant is controlled by a dedicated data acquisition and control system. Each section has a separate control system. Also, some other auxiliary systems are used, for example, cooling and heating systems. And we also have an afterburner to remove smelly gases, emissions. And we have a clean in place system. It's like a pit stop system to quickly clean, for example, the extractors. Since commissioning, so the end of 2018, we processed about 4 tons of fast pyrolysis bio-oil in this pilot plant, producing 4.7 tons of these aqueous pyrolytic sugars. A part of these aqueous pyrolytic sugars we further processed to the sugar syrup, so about 320 kilograms. We also produced 1 ton of pyrolytic lignin, which we converted to about 750 kilograms of solid pyrolytic lignin. And we produced about 16 kilograms of pure extractives. So these fractions, the lignin and the sugars, they will be used for demonstration activities by the bioproduct partners in the coming months. So looking at molding resins, foam resins, foundry resins, and looking at formulations for wood modification. But in the next webinars, these partners will also give presentations on the applications of the fractions and on this product development. We now also started with activities with respect to REACH registration of the fractions to allow the delivery of the extended quantities. If you are interested, it's also possible to purchase fractions produced in this pilot plant for testing. So summarizing the presentation, TCF, thermochemical fractionation, is a flexible innovation 2-step conversion process to transform different biomass resources into raw materials for renewable chemicals and products. TCF uses a short thermal treatment, so fast pyrolysis, followed by low temperature fractionation of the mineral-free liquid product that keeps the key chemical functionalities intact in separate liquid depolymerized fractions. The TCF, in TCF, the minerals are recovered and excess fractions can be mixed back into the pyrolysis oil used for fuel applications. TCF enables the development of a range of bio-based products. Promising results have been obtained, for instance, with these molding resins, foam resins, wood modification formulations, and foundry resins. And the oil fractionation process has now been scaled up to a capacity of 3 tons a day to enable product testing at an industrial relevant scale. So that was my presentation. Thank you for your attention.
Thanks a lot, Hans, for the detailed presentation. We are running a tiny bit late, 5 minutes late, but maybe we have time for just a couple of questions. There are actually 2 questions. I don't know if you can answer about this. There are 2 questions about which experience BTG has with co-feeding fast pyrolysis oil to an FCC unit. It was for Gerard, but I don't know if you can answer about it.
Gerard is still here, so he is able to answer the question.
Yeah, I'm still here. Yeah, we have experience, of course, with several reports have been written about this. We have long experience with Petrobras. So Petrobras have been co-feeding this pyrolysis oil to their FCC, and based on this, we can go out now. And the good thing for us is that also our colleague competitors, NSNU, we are doing the same, promoting the same route. And for us, the good thing is that Technip FMC is also an OEM of FCCs, and they will also give guarantees to the customers about when they want to use pyrolysis, the crude pyrolysis on their FCC.
Okay, perfect. And a question for Hans. Do you apply any pre-treatment to the biomass before pyrolysis for the removal of alkaline earth metals?
No, in the biomass you saw in this presentation, which were used in the thermochemical fractionation, we didn't apply any pre-treatment. So we only do sizing and a little bit drying, but not like you said, removing.
Okay.
No.
And how does the type of biomass influence the composition of the fractions after fractionation?
Yeah, but what you see is that, of course, different biomass types can have a different ratio of cellulose, hemicellulose, and lignin, and you will see this ratio back in your oil. So also in the yield of your fractions quite often. Yeah. But also, for example, if you have a biomass which contains quite a bit of extractives, like for example sunflower seed husks or olive stones, you will also see that that you produce more of the extractives.
Okay, thanks a lot. What's the plan after Biofor Products? Further scale up?
Yeah, at a certain point we would like to scale up. I think the first couple of years we will still run our pilot plant, and then, but it also depends a little bit on the partners, because they have to go to a commercial scale. If they are going to a commercial scale, yeah, then we also have to go to a commercial scale. So I would say within a couple of years.
Okay, and another question, have you already tested how the fractions can be processed into other applications, not including the foreign Biofor Products?
In other applications? Yes. For example, we have tested the pyrolytic lignin in, for example, in paint applications. So in bio-based paints. The pyrolytic lignin, we, for example, developed two types of paints, one on a water base and one on an organic base, and this seems to work quite well. We also did quite a bit of testing on these paints as well, so looking at wood protection and leaching, at the drying rate and degree of drying, smell and color stability, etc. So yes, we are looking also at other applications.
Okay, thank you very much. I think we are now reaching the end of the webinar. So thank you very much for the presentation, Hans. So I think we won't have time for other questions for the moment, but yeah, you have all the details of the speakers, and they will be happy to answer. As I mentioned at the beginning, this is the second webinar of our series. The first one was in September, and you can find the recording on the Biofor Products website. The next one will be in January 2020 about making products out of lignin and sugars. And the last one will be in March 2020 about ensuring sustainability. If you'd like to know more about Biofor Products, you can go to our website and follow us on social media. You can see the details here on this on the screen. And the recording on the webinars and the presentation will be online on the Biofor Products website in the coming days. Many thanks a lot to all the participants and to the speakers, and we very much hope to welcome all the participants to our next webinars. Thanks a lot.